Okay, welcome back. We are going to happily now, I hope you'll think, leave the realm of tectonics and interior processes, and we are going to spend the next several weeks up in the atmosphere, or at least on the surface of Earth, looking at the hydrosphere. And what we're going to be looking at is atmospheric natural disasters, so hurricanes, thunderstorms, lightning, tornadoes, and we'll also look at what it means to talk about cyclones and talk about typhoons. And these are the very, very big natural disasters from a death and destruction point of view. 75% of death and damages from natural disasters in the United States come from these. This is in the United States alone, so elsewhere it would be a different story. But come from tornadoes, hurricanes, and lightning. This is more than earthquakes, landslides, volcanoes combined. So this is a lot of death and destruction here. So when we look at weather, what are we looking at? When you look at the weather forecast, what are you concerned with? What sorts of things? Maybe you looked at the weather for spring break next week, right? Well, yeah. Excellent. Temperature, right? You're looking at temperature. What else are you looking at? What else do you worry about or hope doesn't happen yet? Excellent. Those two things. Excellent. Those are the two things that drive water on Earth. Heat, temperature, and rain or snow, water. So what we're going to do is look at these two things, one after the other. We will look at water and we'll look at heat, because these two things together, again, make for 75% of all the death and destructions associated with natural disasters. So first we're going to do water. What's the chemical formula for water? Yeah, right, everybody knows that, H2O, right? So everyone knows that in this room, I'm sure. I don't know how much you know about the chemical structure, the way that the H's are bonded to the O's. But I'll show you two different diagrams to show you what it looks like in the molecular form. Oxygen here in the middle of this, and then hydrogen here. And overall, water is electrochemically neutral. We're very happy about that. You don't get a shock when you put your finger in water. However, if you could drink yourself down small enough and come over to the hydrogen side of water, you would feel a positive charge. This is significant in all of the properties, virtually all the properties associated with water that are really amazing. If you could walk over to the oxygen side, you would feel a negative charge. So although overall the atomic and the molecular structure of water is electrochemically neutral, we call this a polar or bipolar molecule because each side has a different charge. And we'll look at all of the really, really crazy things that happens when you have a bipolar molecule. So, and this is because of, you don't need to know this number, but there's a 105-degree bond angle. It's not as if, so if my head was the oxygen, the hydrogens are my fists where you're at a 90-degree or 180-degree angle. There's a 105-degree bond angle, and it sets up unshared electron pairs. And we won't get into the chemistry of that for the purposes of this class, but that's the reason why, because of this 105-degree bond angle. My head would be negative and my fists would be positive, which leads to many of the things in my favorite part of this class. The top 10 reasons why water is so cool. And by that, two things. Number one, I don't mean it's temperature cool. And number two, it is not a funny list. Someone always raises their hand and says, Professor Call, that wasn't very funny. So it's not a funny list. Don't prepare to be amused. But I hope that you'll see at the end of this list the unbelievably crazy, aberrant nature of water. Water is unlike anything else on Earth. And we are surrounded by it, right? We're little bags of 76% water ourselves, right? We're drinking it. It's everywhere. Take showers in it. So it's around us everywhere. So we don't tend to have a feel for how amazing this substance is. This is a crazy substance. So the first thing is, again, it's bipolar or polar. I'll show you another picture of that. Because of the 105-degree bond angle, water will exhibit a lot of different properties that no other liquid does. And I'll go through them in the course of this list, but things like it sticks to itself. Remember the first day of classes or the first week of classes, we talked about different types of bonding, and we said that carbon bonded ionically makes graphite, which is your pencil lead, but carbon bonded covalently makes diamond, the hardest substance known to humans. right? This is a hydrogen bond. It's a pretty weak bond, but you'll see it will make for some, again, really interesting properties associated with water. So it sticks to itself. Those dashes means that the plus sticks to the negative, which will then stick to a plus, which will stick to a negative. And that leads into the next cool thing about water, which is that because of this bipolarity, because of the fact that it has this positive and negative side to it, it will, or it is, the universal solvent. It will dissolve everything. That's all that means. It keeps things in solution. The technical phrase for that is it has the highest dielectric constant of any liquid. So if we took a glass of water and put it down here, took a teaspoon of salt and stirred the salt into the water, what would we see? What would happen to the salt crystals? They'd disappear, right? Because they would be dissolved. We looked at this also when we looked at bonding and minerals, right? Halite, sodium chloride, table salt, sea salt. It is bonded together, sodium, chlorine, sodium, chlorine. When water gets in there, the positive side will stick to the chlorine, which is chloride, which is negative in solution, and yank it off of the sodium. And water, again, because of the bipolarity, will stick with its negative side to the sodium, which would be positive in solution, and yank it apart. So it has the highest capacity to dissolve things of any liquid. That's not even up there, sorry. Right there, right? So what does that mean? Well, for the purposes of earth processes, did you ever wonder why the ocean is salty and lakes and rivers are not? Does anyone know why? Anyone want to explain why the oceans are salty? So it's sort of a trick question because rivers and lakes are salty. All natural water has some salt in it because water has a high dielectric constant. But oceans are much more salty than rivers and lakes. Rivers and lakes have about a 5 part per thousand to 0.5 part per thousand salinity, where seawater has a 35 part per thousand salinity. So it's because of the hydrologic cycle, what we'll look at in a minute, what we will continue to look at. Rain falls through the atmosphere, and rain will stick to rocks with its positive or negative side, depending on what it is going to yank off of the rock. And it brings salt through, this is a process of chemical weathering, right? Brings salts through rivers, lakes, streams, groundwater, dumps it out in the ocean. But then when it evaporates as pure water, so the salts are left behind, comes back over. Those of you from last semester remember this is what happens to salinize agricultural soil, right? So it comes back over, picks up some more salts, brings them through this cycle again, leaves the salts in the ocean, and through time the oceans got saltier and saltier. They're not getting any more salty. Right now they're at saturation, 35 parts per thousand, give or take, depending on where you are. So, but it's going on all the time, so that has to be compensated for by salts precipitating out somewhere else, which is where we get these salt flats, right? Because the oceans have all the salt they can take. And rivers, lakes, and stream and groundwater do have salts in them, but it's just their first pass pulling things off. So the oceans are salty because water is the universal solvent. Can dissolve positive and negative ions with equal ease and keeps things in solution. The next thing about water is that it has the highest latent heat of vaporization of any fluid. So this might seem technical also, as with dielectric constant, but what does latent mean? You don't have to think about it in a scientific or chemical term. What does the word latent mean? If you have a latent talent. Yeah. Excellent. Yeah, hidden talent, right? So water has the highest hidden heat of, and you all know what vaporize is. What is vaporize when you're talking about water? How do you get water vapor? Water goes from a liquid to a gas, right? So you have a cup of water and you put it on a heat source and it turns into a vapor, right? We looked at this when we looked at volcanic processes. So of all of the liquids on Earth, water has the highest hidden heat of vaporization. What does that mean? That means you have to put in 600 calories for every gram of water to get it to change from a liquid to a vapor. Now, to be sure, bless you, to be sure, or to be clear rather, when you're thinking about a calorie, like on a candy bar or something like that, you're actually looking at kilocalories. So you don't put in a candy bar's worth of energy for 1 little gram of water. That's a kilocalorie. But it's still a staggering amount of energy. You put in 600 calories to the ocean to get 1 little gram of water to come up molecule by molecule into the atmosphere, to turn from a liquid to a vapor. So as we'll see, this has staggering consequences when we're talking about atmospheric violent weather phenomena. So 600 calories when you go from a liquid to a gas. As we'll also see, the thing that makes for thunder and lightning, right? 3 times hotter than the surface of the sun when a lightning bolt happens. That is going on because water actually goes from a vapor to a liquid when rain falls, and you're releasing 600 calories per gram of water into that cloud. So that is the opposite here, latent heat of fusion. When you fuse, you stick things together, right? So water vapor in the atmosphere in a cloud that comes together and falls as rain, for every gram of that happened, you have 600 calories of energy released into the atmosphere. And again, as we'll see, that makes for explosive warming and incredibly violent things. So 600 calories going from liquid to gas or gas to liquid. It's less when you go from liquid to solid. To go from liquid to solid, you have to remove 80 calories. And to go from solid to liquid, you actually have to add 80 calories. So you warm up ice and it will melt, 80 calories per gram. So that is, again, something that has tremendous consequences when we talk about changing phase in the atmosphere. So these phases, again, it's amazing that we even had these phases at all to be talking about. Water is the only substance on Earth that exists in appreciable quantities in all 3 phases, gas, liquid, and solid, at Earth's surface temperatures and pressures. Nothing else does that. You could think, people always try to sort of think of an exception to this. Oh, what about rock? Yes, there's lots of solid rock, there's lots of liquid rock, right, with magma or lava, but there's not vast quantities of vaporous rock. People talk about methane, methane hydrates, things like that. There's nothing else on the surface of Earth that has 3 phases in large quantities. And if you look at a pressure-temperature diagram, so you put pressure on one axis and temperature on the other, there's actually something called a triple point, a point where these 3 things can coexist. And you may have seen this in the spring when a lake is melting, for example. And so you have ice on the lake, but then there's water beneath the ice and there's steam rising up off of the lake. That's a triple point. They're all coexisting. This is insane. This is really, really amazing. Nothing else can do this. Not even in different parts of Earth, let alone all at the same time. So water is notable because it's the only thing that has the ability to do this. To keep with that lake analogy, we just left talking about plate tectonics, and we talked about how convection cells happen in the asthenosphere, right? So the stuff on top is cooler, is more dense, right? Because the colder something is, the more dense it is, the less rapidly the molecules are vibrating. So it's more dense than the stuff beneath it that's vibrating at a rapid rate. So that's less dense. Top of the asthenosphere is more dense, so they swap places. Everything else, if you take it in a vapor phase will take up as much room as you give it, right? So if I had a little beaker down here and a heat source, and I was boiling water during the course of the class, this whole room would fill with that water. Because again, water will take up, or vapor rather, will take up as much space as you give it. It would be in not very concentrated fashion. The molecules would just be filling up this room, right? Vapor will take up all the space you give it. We'll see this when we talk about ozone layer and ozone thinning. Liquid, what that means is that the molecules are not in a fixed position, but they're touching each other, so they slide past each other. So it takes up less space. Everything else, if you freeze it, now you're in a fixed position, will take up even less space, so it will get more dense. Water, and this is because of that 105-degree bond angle, is the only substance that will get less dense. When you freeze water, when it fixes into position, it expands. Think about if you fill your ice cube tray full of water and you fill it all the way to the top and then you put it in the freezer. What happens when you come back and it's ice? It kind of all ran together, right? So you try to break the ice cubes apart as one big block of ice. Or have you ever tried to put a soda or something into the freezer thinking, I want this to be cold, I'm just going to put it in for a couple of minutes, and you go away and forget about it, you come back the next day. What happened to the can? It's exploded, right? It burst because water is less dense in its solid phase than its liquid phase. Where this is appropriate, again, not so important when we talk about natural disasters, but if you're keeping with this lake analogy, where do organisms go when they are trying to overwinter in a lake around here? Aquatic organisms. Do they leap out onto land? They burrow down into the mud, right? Underneath, they stay warm. Because of this really aberrant property of water, that it is less dense, lakes don't freeze from the bottom up, which is what everything else would do. Solid would be more dense, so there would be a solid forming at the bottom and coming up towards the surface. Lakes freeze from the top down, and so you have, relative to the ice now, a warm pocket at the bottom that organisms, again, can overwinter in. And so if things had behaved the opposite way, where it froze from the bottom up, we might not have life existing from season to season in areas that freeze. So this is a really interesting part, that your ice cubes float. Next time you have a glass of water with ice in it, that ice cubes float is a really amazing thing. So it expands by 9%. Water is also, this is a little bit of like among the highest heat capacity. Ammonia actually has a slightly higher heat capacity, but heat capacity is essentially the predecessor to the third and fourth bullets. Water of all solutions except for ammonia has the highest capacity to hold heat. So this is the adage, a watch pot never boils, right? If you are making the spaghetti that we talked about, when you're making convection cells to make a model of what goes on beneath your feet, you have to wait a really long time for your pot to boil because you have to put in so much energy, right, for the third bullet to get it to change phase. So water is capable of storing vast amounts of energy. Again, this is going to have profound consequences when we talk about thunderstorms, hurricanes, tornadoes. I think I told you this the first day of classes, but Category 5 hurricane has 200 times the global capacity of the globe, to produce energy. So if you wanted to figure out how much energy is in a Category 5 hurricane, we turn on all the generators all over the globe and corral them into one very, very small space relative to the size of Earth, multiply that by 200, and that's the energy in a hurricane. And it is precisely because water has this very high heat capacity. Water also has the highest surface tension of all liquids. Someone once tried to catch me on this and say, what about liquid mercury? Liquid mercury actually has a higher surface tension, but that's a special case, it's a metal. So of all true liquids, water has the highest surface tension. What this means is that it's hard to poke through water. So you might not get a feel for this if you take your glass of water that you have right now and stick your finger in it, right? Big deal, you can poke through it. But what happens if you decide you're going to go out for the swimming and diving team at BC, and you go and you're going to go off the high dive, and so you climb up the high dive at the pool and you run off the diving board. Instead of doing a dive where your head just goes in, you do a belly flop. How does that feel? Feel good? You get up, your stomach is bright red, right? You get the wind knocked out of you. It's very, very difficult to poke through water. to be macabre when they find bodies of people who either have accidentally or purposely jumped off of bridges or off of boats. They find the bodies, all of the long bones in their bodies are broken, because when you go from high up enough and you hit water, it's like hitting concrete. The skulls are shattered, so it's really, really difficult to poke through water. Again, with the lake analogy, which we talked about last semester, there are organisms that take advantage of this, right? Water striders, you've seen water striders. They're not swimming, they're actually walking on the water. They're making use of the fact that this surface, the surface tension, is so high that they can just walk along on it. There's a lizard, right, appropriate because this is BC, called the Jesus lizard, and the Jesus lizard can walk across the water because of water surface tension. When I teach a class called Wetlands, we go to a swamp and I show the students on a field trip these organisms that actually, instead of walking on water, they attach, they're aquatic, so they attach to the underside of water and they swing back and forth. And in this way, they filter feed, so they get their food and they also are able to breathe. They get some oxygen by swinging back and forth in this otherwise stagnant water. And the students all think, oh, that's so cool. They think they're so cool until I tell them what they are, which you know what they are, yes? Mosquito larvae, so suddenly they don't think they're very cool anymore. But mosquito larvae are able to survive into adulthood because they attach to the surface of water. There are also spiders that can do that. So water has the highest surface tension of any liquid. Again, if you have a glass of water and you look at it, you will see that the water is flat for most of the cup, but as it hits the edge, it will come upwards. That's because it's sticking to itself and it actually rises up the side of the glass. If you have a straw in there, look at the level of water in the straw. The level of water in the straw is higher than the surrounding water. Water is pulling up. It's going up on the edges, going up in the straw because of this tremendous, tremendous surface tension. So what about this one? What's the temperature in here right now? Give or take. 70? Okay, yeah. So how are we feeling? Comfortable? More or less, yes. I see some people in tank tops. I see other people wearing their coats. Number one complaint in the office place, it's too hot. Number two complaint, too cold. Yeah, we're really finicky as it turns out. But overall, I don't see anyone in hypothermic or heat stress, right? Nobody's freezing to death or is going to die of heat stress. What happens, if we're comfortable, what happens though if we take ourselves home, we decide, oh, you know, it's Monday, we'll take a relaxing bath. So you go into a big bathtub and you fill it with nice, comfortable 70-degree water. How does that feel? Feel good? No? Why not? 70 in here, we feel fine. What temperature do you like in a bath? Nobody's ever measured their temperature. So maybe you're 98.6, right? 100 degrees, 99 degrees, 97 degrees, depending on your comfort level. Why is this that you're so comfortable in 70-degree air, but you would be very uncomfortable in 70-degree water? It's because air is an insulator. Those who have a thermos, right, for hot liquids. If you cut your thermos open, what you'd see is two walls, and in between you'd see just air. Sometimes they make a vacuum, sometimes there's some insulation and there's some foam, but air is an insulator. So when you're sitting here being 98.6 degrees, air is making sure that you stay 98.6 degrees, unless it gets really, really cold and there's a lot of moisture in the air, right? So you're sitting here being able to stay the temperature that your body wishes to stay at because you're in an insulating fluid, which is air. Water has the highest ability to conduct heat away of any liquid. So what that means is if you take your 98.6 degree bag of water that is your body and you put it into a 70-degree bath, rapidly the temperature is going to equalize. And it is at great cost to you, energetically speaking, to keep your body at 98.6 degrees. You start shivering, you start burning up calories, etc. Also, again, those who fall overboard in water, you will go into shock, and somewhere between, I've read, 30 minutes and 2 hours you can die because you have the whole ocean that's 40 or 50 degrees. You're 98.6 degrees. Your body cannot stay alive if you are 50 degrees. So you go into hypothermia, shock, and you die. It's weird. People describe this who have come close to it as they feel like they're burning up. So strange. But anyway, water will conduct heat away from higher temperatures to lower temperatures and equalize out everything. And the last part of this is that, I don't know, yeah, maybe a stretch. Well, maybe not. We're going to talk about meteorite impacts later in the semester, and we'll talk about this meteorite that was found from Mars, and it may or may not have contained primitive form of life on it. So those who study the possibility of extraterrestrial life forms, we can talk about the Drake equation, that sort of thing, they disagree on many different things. Is there life out there? What would it take to make life out there? We just discovered not too long ago Kepler, the planet that is closest to Earth. It's about 3.5 light years away. Sorry. So it may be that there's life out there. Many people think so. But what they all agree on is that in order to have extraterrestrial carbon-based life forms, you have to have a planet that has vast quantities of liquid water or free water. Otherwise, you could never have life form. And so that is something, again, we'll revisit in a sort of sideways way when we talk about meteorite impacts. But it's truly the reason we're here. From a short-term point of view, right, if you're deprived of water, you die pretty quickly. Organisms do. And from a long-term point of view, it is the case that we don't think people could ever, or humans, any sort of life form could survive or originate without lots and lots of water. So I hope you have a good feel now for this aberrant substance that water is. It is extreme in so many ways. And these characteristics of water, what are going to make for the violent weather phenomena we talk about. So now we will look at the heat part, right? Because when we're looking at a weather forecast, we look at water. Is it going to rain? Is it going to snow? Is it not? Is it going to be cloudy? And then we look at the water. Then we look at the heat. What's the temperature going to be? And temperature on Earth, here's the hydrologic cycle, 1.36 billion cubic kilometers of water cycling around on the surface of Earth. It's an exogenic cycle, exo meaning external, genus or genic meaning originated, come from. So it's an exogenic cycle. It gets its energy from elsewhere, and that elsewhere is the sun, right? So the sun shines down on the surface of Earth, and it will impart vast quantities of energy to get this water to change from a liquid or a solid to a vapor, or a liquid then a vapor. And it will come up into the atmosphere where it will rain or snow back down onto the surface of Earth, maybe temporarily locked in lakes, but most of it will come into groundwater. Some of it will stay rivers, dumps back into the ocean where it starts over and over again. So the salient point of this is that heat is what's driving the water around on the surface of Earth. And weather is going on in that atmospheric portion of the hydrologic cycle. So another question, we talked about this also a little bit last semester, so if you know the answer, hold back for a minute. I'm looking for the wrong answer here. I'm looking to dispel a popular myth. So if you don't know, shout something out. You guys are a quiet group. Why is it hotter at the equator than it is at the poles? Have you ever thought of this, about this? Yep. Thank you, excellent, right. That's not the right answer, which is exactly what I was looking for. Thank you, it's amazing. People think, oh, it's hot at the equator because it's closer to the sun. That is not the situation at all. Now, does anyone know the right answer? Yep. So close, not the axis, but the tilt, exactly, the curvature of Earth. Excellent, right. So let's draw this. Yeah, let's draw this. Let me see. Bring up one of these screens up. And I'll turn the lights on for 1 minute. And watch, we will have no chalk now. It's a bad setup here. Yeah, maybe I won't be able to draw because there's no chalk. It's a terrible setup. The people that put chalk there, it drops behind the board. Let me look here for 1 second. Okay. Let me see if I can, yeah, all right, we'll try to do that, if you can see it. No, all right. So this will be, okay, this, imagine Earth being like this, if you can see this little smudge mark. The smack that I just gave to the atmosphere here, the sun's way over here, shining its rays onto Earth. I'll lick my finger, that's really gross, but all right. So what happens when you have Earth at a perpendicular angle to the sun's rays is you have exactly that width of this. So if this is 100 miles, we'll say, 100 miles of a sunbeam hits exactly perpendicular to the Earth at the equator. But if you're looking up at the poles, so now you have this curvature. Now what you can see, this will work, is that from here to here, crazy teaching, right? From here to here is probably double the distance that you saw here. Because what's going on is the sun's rays are hitting at the equator, perpendicular. The sun's rays are hitting up towards the poles in a very, very oblique fashion. If you think about the North Pole, the sun doesn't hit at all, it just passes straight over. So this is the reason why it's cold at the poles and hot at the equator. Here's a picture of what I'm talking about. There's the equator, hits perpendicular. There is the northern regions, or southern regions just as easily. It hits at an oblique angle or passes straight over. You can do this yourself in another little home experiment. Take a basketball, take a flashlight and a friend and go into the closet where it's completely dark. Have your, why people laugh about that? What are you doing? I'm not coming. So here's your ball, here's your friend with the flashlight. Don't touch each other. Stand over here and shine the flashlight on the basketball at where the equator would be. If the equator were on the basketball, what would you see? What would the footprint of the light be? It'd be circular and bright white, right? Now, as you move the flashlight up the basketball, you're not doing this because that's not how the sun operates. The sun is this immense object and all the rays are going straight. As you lift the flashlight up to go more and more towards the northern part of the basketball, if the basketball were Earth, what happens to that bright circular white sunbeam? As you go up, it starts to spread out, right? It gets less bright. Covers more of an area, but it's a darker, then it will start to turn orangish, right? It won't be the bright white sunbeam. That's exactly what's going on here. The secondary effect to this is that, down. The secondary effect is that you have the atmosphere. We'll spend a lot of time in the atmosphere during the rest of this class. The atmosphere is this thick blanket of gases, and so when the sun's rays come in through the atmosphere, they start to scatter. And so when you're at the equatorial region, you go through the least amount of the atmosphere. And as you go up to the higher regions, you're going through it at an oblique angle. So you go through a lot more atmosphere. So there's a lot more scatter. So that's a secondary effect. But essentially, the reason for it being hot at the equator and cold at the poles is because the sun's energy is less concentrated. So I don't love this picture because I wish it were the basketball analogy, but you can see what's going on here. When the sun hits the basketball at an angle, the footprint gets smeared out, and so it's over a larger area. So talking about the tilt, Earth tilts, and that makes the seasons. So we're not talking about tilt, we're talking about the curvature of Earth. There is the point now that it's summer in the northern hemisphere because the North Pole is tilted towards the sun. So you can see, yes, there's a little bit of a distance between the equator and the North Pole, but that's inconsequential relative to this phenomenon. At the place where you're hitting straight on, hottest, and at the places where you are hitting the most diffuse, it will be the coldest. You see, because of this tilt, right, the South Pole now is in constant darkness first period of several days. No sun hits it at all. And then the tilt will go back and forth. Again, we'll talk about this actually when we talk about climate change and the seasonal cycle. So what does this mean for us? Well, this is where last semester, or if you take this class next semester, we talked about this very phenomena. We talked about it because we wanted to know where life is on Earth. Why is there a desert here? What kind of animals and plants are in a desert? Here's where we diverge in this class. What we're looking at now is this sets up violent storms for a reason that we'll see. This is a diagram that may make no sense to you right now, just looking at it all at once, but let's tease it out and see what does this mean for natural disasters. On the x-axis, we have latitude, and that's on Earth. So it's as if we unwrapped Earth, right? So if I'm holding Earth right here, my finger is the North Pole, this finger is the South Pole, my head is the equator. We're just unwrapping it. So here on my right hand, we have the South Pole, left hand, North Pole. So just unwrapped Earth, you're going from the South Pole all the way to the North Pole. On the y-axis, don't get too hung up on these units. The units aren't important. The trend here is important. On the y-axis, we have a measure of energy per unit area per unit time. What does that mean? Well, that means that if I take this table, I want to measure how much energy is hitting this table from the lights above. I could put in some sort of light detector, and for 1 square meter, have a little light detector mat, turn it on, and figure out for 1 second, turn it on for 1 second, and then shut it off, figure out how much light hit that 1 square meter in a second. So that's all we're doing. We're figuring out how much of the sun's energy hits a square centimeter of Earth per minute. So that's all we're looking at. How much energy has come in per square centimeter per minute. So now let's look at the solid line here. That's incoming sunlight. We already looked at this, right? We said because the sun's rays hit perpendicularly at the equatorial region, that's where the most energy comes in. So from about 30 degrees south latitude to 30 degrees north latitude, we have about 0.45 calories per square centimeter per minute. Again, number not at all important. What we want to go away with regards to this diagram is the trend. As you go, and again, those of you from last semester, remember 30 degrees north and south latitude, there's deserts, right? Wegener, talking about Wegener this semester, he knew that there were deserts at 30 degrees north and south latitude, right? So you have this energy that is about 0.45 calories per square centimeter per minute from 30 degrees north to 30 degrees north to 30 degrees south. And then as you go towards the poles, it rapidly tapers off, and it's symmetric, right? To less than 1/10 of a calorie per square centimeter per minute. Still, you should not really understand the point to this, but understand that trend. Now we look at the dashed line, and that dashed line is outgoing energy. So energy that's re-radiated back out into space. And what you see is it's essentially a subdued replica of the incoming sunlight, right? So it does the same thing, only the high's not as high, the low's not as low. So same thing. The heat lost back out into space at the equatorial region from about 30 degrees north to 30 degrees south latitude is about 0.3 calories per square centimeter per minute. So now we see a situation on Earth where heat is being gained all the time. You have 0.4 calories coming in, 0.3 calories leaving. This would be a good example for, or a good situation for, say, your bank account, right? If you have $1,000 in your bank account and you're always adding $400 and your bills only come to $300 a month, your bank account balance is going to grow and you'll get rich. But it's not such a good situation on Earth, right? If it's always getting hotter and hotter and hotter in a region, and Earth, as we know, is 4.6 billion years old, it could be that we end up with equatorial regions of positive 30 trillion degrees, which obviously is unsustainable. The opposite is true at the polar regions from about 40 degrees south latitude to the South Pole, 40 degrees north latitude to the North Pole. That dashed line comes down a little higher than 0.2 calories per square centimeter per minute. So you see that more energy is leaving than is coming in. So that would be a bad situation for your bank account, right? You have some money in there, but you're only making $300 a month and you're paying out $400 in bills. Pretty soon you better hope that you have cash reserve or get a raise because you're going to go negative very quickly. Likewise, in the polar regions, this is not a great situation because the temperature dropping all the time for 4.6 billion years could be, now we're in negative 10 trillion degrees. And this graph is what's going on Earth. This is exactly what is happening on Earth. Heat's being gained in the equatorial regions, heat's being lost in the polar regions. But we know, obviously, it's not negative 10 trillion degrees at the equator, at the poles, and positive 30 trillion degrees at the equator, so why not? What's going on to make the temperatures not this extreme? Excellent, excellent. Convection. You're transferring, the same thing that's going on beneath your feet is going on above your head. Thank you. You're transferring the heat to the cold. You're transferring the cold to the cold to the heat. And it's this transfer of energy that's going to drive severe storms, that's going to make for violent weather. And here's where we can start talking about all of these cool atmospheric phenomena like the jet stream and like these convergence cells and all sorts of really neat stuff. But let's start very, very simple. Convection. We will look at a diagram of what is not happening on Earth. Well, then why are we looking at it? Well, we're looking at it because we're going to start simple and then we'll build up to reality. This is what would be going on if Earth were not spinning and if there were no mountains and oceans and all sorts of features on Earth. If Earth were just this solid, homogeneous ball that we're not rotating, what would happen is at the equator, where the temperature difference is the greatest, the sun is beating down on the ocean, right? 600 calories per gram being put in, vast amounts of water evaporating and going up, up, up to the top of the atmosphere. So this is the starting point of the convection cells, again, very similar to what's going on beneath your feet. So this atmosphere, so this hot, hot vaporous water is coming up, 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 gets to the top of the atmosphere. It's got to move along to get out of the way of the stuff that's constantly coming behind it, or I should be doing it this way, right? So it's moving along the top of the atmosphere, continually being pushed by stuff coming behind it. But as it progresses to the northern part of the northern hemisphere, or the southern part of the southern hemisphere, that heat that was so tremendous that came up and is going starts to slow down. So the air mass gets less dense. By the time it gets to the North Pole, or the South Pole, same thing, north versus south, the air masses are all converging like spokes of a bicycle wheel coming together. And it's also very dense because it's been tremendously cooled by the fact that now you're in a situation where the sun's energy is no longer concentrated. So the air masses come together. If you could tip this towards you, you'd see, again, sort of looking like a donut almost, spokes of a bicycle wheel coming together, dropping down because it's very dense, and then it hits Earth and it spreads out again like spokes of a bicycle wheel in every direction and getting out of the way of the stuff that's constantly coming behind it. But then it comes down on the surface of Earth where it progressively warms because the sun's energy is becoming more and more and more concentrated till it gets back to the equatorial region where this air mass is rising up and it joins that and it comes around. So you have these two cells that are going, so this is a sphere, so we can put the coordinates on it, from 0 degrees, the equator, to 90 degrees, the North Pole, and 0 degrees, the equator, to 90 degrees, South Pole. So these two cells that are just doing this because of the previous slide of those temperature differences. And as we said, the water that we looked at, which is so good at holding heat, at absorbing heat, at transferring heat, is the mechanism by which this heat is transferred. If we didn't have so much water in the atmosphere, this heat wouldn't be transferred in the way that it is. It's because water is so good at conducting heat, at holding heat, and transferring heat that this happens. So yeah, this convection cell going from 0 to 90, 0 to 90, through the northern and southern hemisphere. So again, this is what would happen if Earth were not spinning, there were no mountains, there were no oceans. But what the reality is, to add one layer, is that Earth is spinning. And you wouldn't think so, but this is a highly complicated technical phenomena that, so in physical oceanography or in dynamic Earth, when you have a lab, we spend weeks on this called Coriolis force. You guys are lucky you don't get to deal with Coriolis force in great detail and get super confused. All you need to know about the Coriolis force is that Earth is spinning. That's it. And so Earth is spinning at 1,037 miles per hour. Don't even need to know that number. Spinning at 1,037 miles per hour, but Earth isn't a cube, right? So it's not spinning all at 1,037 miles per hour. Where the circumference is the largest, that's where it's spinning at 1,037 miles per hour. As you go up, the circumference lessens, so it's spinning at a lesser and lesser rate as you go up the northern hemisphere till you get to the North Pole, where it's not spinning at all. It's rotating about its axis, but that's a 0 mile per hour rate of spin. So we go from 1,037 miles per hour to 1,000 to 900 to 800. So I can never do this, but I always try. So if I try to, with my finger here, trace the circumference of the equator, and then up here, the circumference where we are, say. This finger, my left finger, is going to move a lot more quickly than my right finger to make that revolution, right? Because this finger is not traveling very far, and this finger is traveling really quickly. So the point is that Earth is spinning, but it's spinning at different rates as you go up Earth. And that is called the Coriolis effect, Coriolis force. And we are actually out of time, so let's pick it up here next time, and we'll look at what happens to those convection cells when we start Earth spinning out from under them. Yes. We had the test Fridays, so yes, this and I know, I hate to test you on something on Friday that we did on Wednesday. Yeah, I think it will be.